Hi everyone, this is our unit on alcohols and ethers. Let's start with naming alcohols. So by now you know alcohols are molecules containing the hydroxyl group, OH. So normally for naming, we always go with the longest chain. It should include the alcohol, in most cases it will. Sometimes you can name the alcohol as a hydroxyl substituent, but you'll see that more as we add other functional groups. For now, your molecules usually are going to, if they have OH, will be named as the alcohol, or if it's a benzene ring with an OH, then that's named as a phenol, Phenol, because this is a phenyl group, so that's called a phenol. Otherwise, and then here we have a diol, so you see some variations on that. But go with your longest chain and go with alcohols having a higher priority than alkyl halides or alkenes even. So you want to try to name it so that the OH group gets the lowest number possible. Okay, so let's try A. So you want to find the longest chain. You want to give the alcohol the priority. So let's number this and then come up with a name. Okay guys, so for part A, I'm seeing a chain of 6 carbons with the hydroxyl getting the lower number 2 rather than starting this way. And then that puts the bromines at 5, but that's okay because OH has a priority. So that means it's going to be a 5,5 dibromo where we alphabetize based on B, 2-methyl, and then hexan 2-ol. And you could also do, instead of hexan 2-ol, you could say 2-hexanol. That's also acceptable. Now there's no stereochemistry on this one, but if there was, we would specify the stereochemistry here. So we would say R or S for chiral center, however many chiral centers there are. Okay, let's move on. Okay, let's try B now. Go ahead and look for your longest chain, and for this one you're going to name it as a diol. So either butadiol, pentadiol, hexadiol, and you want to specify numbers for where the OHs are, because the diol could be 1,1, 2,2, 1,2, 1,5. You know, you have to specify where those OHs are located. For part C, remember to name this as a phenol and try to use the lowest numbering possible. For D, you want the lowest possible number combinations here as well. And for these guys, remember you want to keep the OH to be the lowest possible number also. All right, go ahead and give those a try, and let's see how we do when we come back. Alright guys, so for part B, I've numbered the longest chain, and I see it's going to be a pentadiol of some kind. And I want the lowest numbers to be with the OH groups. Then I noticed 2 chiral centers here, so let's take care of those. So first, this is going to be my 1. Then I look at these 2 carbons next, and their next heaviest is O here, and this one is actually, I thought it was a bromine at first, but that's from the previous problem. So sorry, I didn't space that correctly, but this is a CH3 here. So an O versus a C, so O wins. So this will be my second priority. So this will be 2 and this will be 3. So this will be 1, 2, 3, so that'll be S. And then for this guy over here, this will be 1 here because I have an O next. So these are a tie. And then you look at the next heaviest one. So this will be 1. And then I have this methyl versus this carbon with, it has carbons attached. So this is 2. And then this is 3. So 1, 2, 3 like that. And in both cases, my number 4 priority, which is hydrogen, is in the back. So this one's going to be R. So let's put that in first. Now I've got methyl groups here and here. So I want to say 3, 4 dimethyl. And then I'm going to add my penta dash 1, 2, because I need to say where these diols occur. Carbons 1 and 2. Penta 1, 2 diol or 1, 2 pentadiol is fine. And the problem on this one is actually the OH group wasn't in the original problem. I just added it there. For part C, since we're naming the phenol as the functional group, I want to make sure the phenol gives the alcohol group the priority. So I can number that 1. Even though you've learned for cycloalkanes that you want the lowest possible numbering combination, for phenol you want this OH to be the lowest possible number. So this is 1. Because it's called a phenol. Okay, so that's a little different than what you had before. So that means that I can go this way or I can go this way. Either way, I'm going to get a 2,6-diethylphenol. Okay, so that's a little bit different. Now back to alkanes, you can just choose the lowest numbering possible for this because I'm not restricted to calling this a phenol because this is not aromatic here. So this is going to be 1, 2, 3, 4. That gives my OH group a lowest number, and a lowest combination of numbers is 1, 2, 4. So this turns out to be S 1, 2, 3 counterclockwise. So S 2, 2, 4, 4 tetramethyl cyclohexane 1-ol. So you want to pick its, put the 1 there just to emphasize. You can do 1 cyclohexanol or cyclohexane 1-ol, but it helps to have that 1 there because you really want to specify with alcohols where is the OH group. Now, if you guys recall about pKa, we're referring to these acidic hydrogens. They're not super acidic. They're, water has a pK of 15.7. So these are, alcohols in general are similar to water. So water is 15.7 pKa. Alcohols are what I think of as 16-ish. Cyclohexanol is a specific alcohol that has a pK of 18. So this is weaker than water's hydrogen because water is pKa of 15.7 or about 16. So this is going to be weaker than water. And then over here, this is stronger than water's hydrogen. Even though they're both OH groups, this one is much more acidic. So how do we explain why phenol is a stronger acid than cyclohexanol? Well, I think we need to look at their conjugate base's stability. So let's do that. So to get the conjugate base, you just remove the proton. So I'm picturing taking a base and removing this proton or removing this proton here. Here are the 2 conjugate bases respectively. And then once I have these conjugate bases, I want to look at their stability. How is their stability different? And if you notice, this one's going to be more stable. I think it has something to do with this pi system here. And that's because of resonance delocalization. So I've got one resonance structure here from this guy. And so this is going to look like this. And I challenge you guys to come up with 2 other resonance structures that helps to explain how this negative charge gets distributed over the entire ion. Alright guys, so here we are with the other resonance structures. You can show these electrons getting pushed here and depositing on this carbon as well as depositing on this carbon over here. So it's important to think about that negative charge buildup on this molecule is just here for the cyclohexanol's conjugate base. It has nowhere else to be spread out, so that concentration of charge makes this a strong base. But when you look here, this negative charge appears to be distributed particularly over these carbons by resonance, and that demonstrates that the charge is actually spread out. Alright, and that helps to stabilize this molecule. By spreading out the charge, you don't have those hot spots where it will react. Alright, even though it doesn't seem like a big difference, we can explain small differences like this as well. So this alcohol ethanol has a pK of about 16, whereas tert-butanol has a pKa of 18. So which of these is a stronger acid? So what this is telling me is that ethanol has a lower pKa value, so it's a stronger, slightly stronger acid, 100 times stronger because the difference is a logarithmic factor of 2, so 10 to the 2, so 100 times stronger than tert-butanol. So even though 2 pKa units doesn't seem like a lot, it's actually 10 to the 2. So if we look at ethanol, let's look at its conjugate base, which is ethoxide. Tert-butanol's conjugate base is tert-butoxide. And the main difference between these, they both have a negatively charged O, The main difference is what the R group, the structure of the R group is. So here I have a primary, but here I have a tertiary. So what's going on here? So for the R groups I see here, they all carry electrons. There is some induction because the O is pulling that negative charge over to it. So there is a little bit of flow that way. So this is called induction, is that pull of electron charge toward the O because of O's electronegativity. So by induction, we think of the oxygen as being more negatively charged when there's more R groups nearby. So I'm going to say by induction, the electron density gets concentrated more on this O than on this O because this one doesn't have access to as many R groups nearby. It has this one, and it might have a chain, but it's not the same as having them really close by like here. So the more branching you have, the more immediate that induction is felt. So here we would say O is more basic in this case, which means a stronger base leads to a weaker conjugate acid. So the weaker its conjugate acid, the higher its pKa value, and that's what we see with ethanol and butanol. All right, so let's look at branching again. The more branched you are, so if you have 3 R groups, you're tertiary. If you only have 2 R groups attached to the carbon, it's the alpha carbon. Alpha means it's the first carbon attached to the group of interest. So for all these OHs, it's not how many R groups are on the OH, it's how many R groups are on the alpha carbon of the OH group. So we're looking at the neighboring carbon of the OH group. So we have tertiary if you have 3 R groups, secondary if you have 2 R groups, and primary if you have 1 R group. So if you look up here, ethanol is 1 R group here, right here, so this is primary. And then here, this one has 3 R groups, so this one is tertiary. So it's good to just be able to talk about primary, secondary, and tertiary alcohols. That kind of classification will help you remember certain things like SN2 reactions. So alcohols can be prepared by SN2 or SN1. So we have X, a halogen, replaced by an OH group. So this is how to make alcohols. So there's different pathways we can take. If the R group is primary, so we have a primary alkyl halide going to a primary alcohol, will you likely have SN1, which goes through a carbocation, or SN2, where you have a concerted nucleophilic attack and leaving group leave at the same time? So this is a review of Chem 261, but I think you remember that if the nucleophile is not doesn't have too much steric hindrance for attack, like a primary, then that will attack at the same time that this leaves. So it's going to be more like SN2. The alternative pathway is if X got released first, then this would make a carbocation, but we saw that there's not a lot of induction with a primary, so then you would have less stabilization of a primary carbocation. So if it's tertiary, then you would, by induction, have more stabilization of a carbocation. So in that case, the mechanism would likely be SN1. And then if it's secondary, we see it actually is more similar to primary, but you can see either mechanism or it goes both ways sometimes. You've also looked at pi bonds as our nucleophile, attacking these different reagents to get an OH group. So notice that with the dilute acid, you get addition in the Markovnikov position, as well as with oxymercuration reduction, you also get an OH here in Markovnikov. Don't forget that the acid will result in carbocations, so that could result in rearrangements then. So this is through a carbocation intermediate, whereas this reagent goes through a cyclic mercurium ion, so then your water attacks Markovnikov here to open that up, and then the second step is to get rid of the mercury with NaBH4. Our other option is to put it on the less substituted side, the OH group, and so that's called anti-Markovnikov, regioselectivity, and that has to do with this reagent here, BH3 prefers to add on this way in anti-Markovnikov fashion like this. and then you're going to have the BH2 group eventually get replaced by OH group in the second step. So the key to this part is really being able to see how you can transform this group into an OH occurring here or here based on which reagents you use. So take a moment now and review these reactions. It's easy to forget them. So now we've arrived at some places where we can prepare alcohols. So how do we get to an alcohol from these different starting materials? So I want you to think about substitution in this case because you have Br and you're just replacing it with OH. So think about whether it's going to be SN1 or SN2 and what reagents do you need to get that to happen. For the second two reactions, these are electrophilic addition reactions. So this is chapter 7, this is chapter 8. So think about those things. Think about Markovnikov, anti-Markovnikov in this case. Let's check our answers in a few minutes. Okay, hopefully you guys found that this wasn't too bad. For this first one, this is tertiary, so we want the leaving group to leave first and then have attack. So you want to usually pour nucleophile for SN1. So I just chose water because water will put a water group on here, and then another water will come by and deprotonate that. So water should be sufficient for this reaction. Alright, for this second one, we want the nucleophile to come in and kick this out, so hydroxide as a nucleophile is fine. This will be like an SN2 reaction because it's primary alkyl halide. For the second one, we want Markovnikov addition, so we want the OH here. So there's two methods for that, either acid and water, or you could say dilute acid, or you can use oxymercuration reduction. For this one, we want anti-Markovnikov, so we're using the hydroboration oxidation reaction here.